Is on page 358 is the non-soidal waveforms, and the one that we're going to be looking for is the clock pulse or the square wave. So on our MyDAC, I got my MyDAC plugged in. I'm going to open up my NILvis, and what I'm going to do is I'm going to open up two things. So this is going to pertain to all your labs or anything. So whether you're in digital or just looking at AC, it's all going to be the same thing. So what you want to do is you want to click on your function generator. So here's our function generator, and that's what I was saying is the same thing as this. The only difference is that we can only go up to 20 kilohertz. Okay, so that function generator is the same thing here. Then I have different choices of what type of signals I want. I can have a sine wave, a triangle wave, or a square wave. Then I can adjust what I want my frequency to be. So I can go from 200, I don't know, looks like, I don't know what that number is. 200 milli, so down to 200 millis to 20 kilohertz. So I can go really low frequency there. So 0.2 hertz. Okay, so I can go down to 0.2 hertz up to 20 kilohertz. I can adjust my amplitude, and you can see that the units here represent that it's in volts peak to peak. So here's what I was talking about. Here's my units, it's volts peak to peak. So I want to keep everything else, calculate everything else up in volts peak to peak if I'm using my function generator. Then I can put in my DC offset, and we'll take a look at that, what I was talking about on that. Then there's some other really neat things that we can do when we get into when we're working with our components. So we're going to be working with capacitors and inductors during the AC. Now, when we were working with DC and we were working with just resistors, those are what we call passive components. If I take a resistor out and I measure the resistance, it always stays that resistance, right? No matter what I do to the voltage, whatever I do to the frequency, that resistance of that resistor is always going to stay the same. Well, now we're going to be working what we call with reactive components, capacitors and inductors, and the resistance of those components are going to change depending on what the frequency is. Those are going to be our frequency response of our components. So for example, if I have a capacitor in a circuit and I put a very low frequency in there, I'm going to have a very high, what I call X of C, a very high resistance. Okay? If I put in a very high frequency across that capacitor, I'm going to have a very low resistance. And so that resistance is going to change depending on what our frequency is. And so we have these things that we call sweep settings. I can vary my frequencies across it, and it'll change my frequency over a certain amount of time. And then I can watch what happens to my voltage going across my components as it changes frequencies. And we'll talk about that later on when we get a little bit more into what's going on here. So anyways, this is kind of our function generator. So basically what we're going to be looking at is just using the sine wave. If you're in digital, you're going to want to select the square wave. And then you're going to have to set up a certain amount of frequency, set up an amplitude, and then you're going to set up a DC offset for your circuit. So to measure that, so then again, like I said, now what we're going to be using is in AC, we're always going to be using our oscilloscope. So here's, I've been talking about this oscilloscope. And this is what our oscilloscope looks like on our screen. Let me grab a real one here too.
Should you just read it from internally? I hope so. Like I said, I didn't look at it yet. I haven't opened up.
Well, like I said, I tried last night and my computer doesn't work.
So when I'm talking about an oscilloscope, this is what I'm kind of talking about. Here's what a real oscilloscope looks like, and the one on our MyDAC is the same thing. These ones here, they can have up to 2 channels, so we can measure 2 different waveforms at the same time. Same thing with the one on our MyDAC. This one can go up to, these are brand new ones. These ones I think can go up to, these can go up to 100 megahertz. These are brand new, so we haven't used them, so These will be kind of neat. These ones all colored and stuff like that. A whole bunch of neat little functions on them. So there's a lot more that you can do on this one than what you can do with the MindDAC. The MindDAC, we're going to really learn how to use our data acquisition when we're done with AC, because the way we do things here, we have a math function on here. Here we have to wire it up in a different way to get our math function. So this one here has a lot of neat little functions. It has cursors for measuring. We can acquire the signal, so we can stop the signal, because if we have a signal that's going to come in and it's only going to last for just a couple of microseconds, you know, it's too quick for us to see it, but we can acquire that signal, so when that little pulse comes in, the oscilloscope will get triggered, and then take a snapshot of that picture so we can do any of our measurements and stuff with it. But we'll talk about that a little bit more in depth tomorrow. All I really want to do is kind of get the guys that are in digital and then going on their digital circuits here so they can see their clock pulse, and then you guys can see what an oscilloscope looks like. So when I'm talking about an oscilloscope, you know what I'm talking about. All right, so when I plug in my MindDAC and I open up my function generator, it's going to call out, here's the device, it's going to be MindDAC, and then it's going to say what the signal route. So the function generator comes out of that AO0, or I can have it come out at AO01. Okay? So for the most part, we'll just come out of our AO0. And when I'm talking about that, again, when I talk about A00, what I really want you to do is I want you to come out of, so here's my MindDAC. This is in Multisim. You can actually bring up your, you can do a couple of cool things with Multisim, but there's the MindDAC in Multisim, and you can actually simulate your circuit using the MindDAC. You can wire right up to this MindDAC, come up with your circuit. You can run the simulation on it. It'll simulate it. It'll calculate all the currents. It'll display all the waveforms and stuff like that. And then what's kind of cool about it is that you can actually go into your oscilloscope and let's see, where is that here? Let's see it off the top of my head here. But anyways, what you can do is that if I have it hooked up going through the Multisim and have it going through my function generator, I can actually display what my waveform looks like in my simulation, and then below it I can measure my actual circuit. So you can compare the two signals and stuff like that. So there's some cool stuff that you can do with it if you want to take it that far. But anyway, this is in Multisim here. If you want to find out where to get your MindDAC, what you do is you go under File, go to New, and then you can go to the NI Elvis 1, 2, and then here's the MindDAC design, and that'll bring up this page here. And then again, you can put in a component and wire up to it and stuff like that. Okay, so so as we get a little bit more into AC and stuff, we're going to get away from graphical designs. We're going to use more on schematics and stuff, and not do so much on the graphical designs like I did in DC, so we can get started. So when I'm talking about AO0, those are my analog output. That's what the A0 stands for. It's an analog output, and then it's channel 0. Now remember that these two channels, those are going down to our op amps. Channel 0 and channel 1 are going down to our op amps. And then the outputs of those are going to our two buses, okay? So when I'm talking about A0 channel 1 and channel 0 channel 1, I want you to use those buses coming out of the op amp so that we have enough current going through there. Alright, but for our digital signal here, I'm just going to... So our analog output was coming off of... so our function generator is coming off of our analog output, channel 0. And when I set up that function generator, then there's going to be a signal coming here. We'll just put in a sine wave here to begin with. And then to measure that signal then, what I'm going to be using is my AI channel. That stands for analog input. Then you're going to see -1, and then 1 minus, and then 1 plus, and then there's a 0 minus and a 0 plus. Those are our two different channels. Those are what we call differential channels. So it's a little bit more complicated to wire up the MIDAC for grasping the concept of it, but once you understand the concept of it, then there's some benefits of having the MIDAC over the oscilloscope. And we'll talk about that as we learn a little bit more about the oscilloscope and everything. So what I want to do is I want to just come off of my analog output, my channel 0, and I want to measure this signal coming off of it. And so what I'm going to do is I'm going to come off of my analog input, I'm going to go off of channel 0, my analog input, channel 0 plus, and I'm going to just go right into my analog output, channel 0. Now I always need a reference point when I'm referencing a signal. I'm always going to need a reference point, my point of reference. For this particular case, it's just going to be my A drum. So then what I'd have to do then is on my other differential output, I'm going to have my inverting and my non-inverting. I'm going to take my inverting, which means that it's my negative side, and I'm going to tie that one I'm going to just plug that right into my A drum. So that's all I already have it hooked up that way. So I'm just going to measure what's coming off my function generator. So I'm going to turn on my function generator. I'm going to turn on my oscilloscope. And in there I can see that I already have my AC signal. If I change it, it'll give me a triangle wave. It's going to be a square wave. Okay? So that's my graphical representation of what's coming out of my output. This is what's being outputted, and then this is measuring my output. So this is the graphical representation of what's coming out of A0, 0. And I'm using my signal route is so on my source 1, I'm using my analog input, channel 0. So one thing about it when you're working with oscilloscopes is that you can see that the picture keeps on scrolling. It doesn't know where to trigger it. So I'm just going to go and I'm going to tell it to go off the edge. So when we're working with oscilloscopes, we have to tell it, since it's a graphical representation of the signal that's being outputted, we have to tell the oscilloscope when to start drawing. All it's doing is it's drawing. It's just whatever it sees, it draws it. So we have to use what we call a trigger, and we have to tell the trigger when to trigger. Well, it's just going to trigger off the edge. It's going to trigger off one of the edges, and it's going to do it when it goes from a low to a high. So if I can't see it. That's bad. Oh, there you go. I didn't keep it moving. So there's two crosshairs here. I got one that's right here, and then I got one vertical and one horizontal. That crosshairs is when it's telling the oscilloscope to start to draw the signal. The signal's actually starting right here. It's doing it at the 0 reference, because that's what I told it to be at, the level. So right when it goes right above 0, it starts drawing this picture out. And it keeps on going, and every time it goes just right above 0 on a rise, it's going to redraw it out. Okay, so we'll go over this a little bit more tomorrow, but that's what an oscilloscope is. It's just a graphical representation of our signal.
Can you try one for me quick?
Yep.
Use square wave
Yep.
at a frequency of 1.5 hertz.
Okay.
Put your DC offset at +5.
Perfect one. All right.
And then just kind of mess with the amplitude, because I got my digital circuit to work by going all the way up on the amplitude. And that's the only way that I counted correctly. I'm just
and that's
what the hell was going on.
Well, now you can at least see what's going on. So what we want to do is so here's what you're going to want to do: set up for yours in your digital. So we have our function generator. We want it to be a square wave. You said at 1.5 hertz?
It's where, I don't know, seemed all right, yeah.
You want you to do 60 hertz?
Just so I can see the readout.
Okay. That's pretty slow, so that's easy to see. Yeah, you'll be able to see that turn on and off and stuff like that. So 1.5 hertz. And then he probably wanted a plus 5 volts clock pulse, right?
Yep. I believe so. Your guess is as good as mine.
Yeah. So what the signal looks like, so what he wants you to have, so we're going to just rough sketch our signal. This is what we always do anyways when we're trying to figure out new signals or anything like that. We draw what we really want. So what he wants you to have is 0 volts DC up to a plus 5 volts DC. Okay, so he wants you to have it. And so what we have to do, when I first turn on my function generator, and I have a DC off of 0, what it's going to do is it's going to take my voltage peak, and it's going to go half below my 0 volts DC, and then half the volts above the voltage DC. So when I first turn on my function generator, what it did with this signal is that right here is my 0 volts DC. Here's my DC reference right there. And then it brought it up to a plus 2.5 volts down to a negative 2.5 volts. Okay? So that's what your function generator is going to do. So what we want to do is we want to shift this all up. So if I want to get this, so this negative never goes negative, what I want to do is I want to give what we call a DC offset. That's my DC reference. So what I want to do is I just want to add 2.5 volts up to it, and then that'll raise that signal up. That way then it'll make it, what it does then is it gives me my 0 volts reference, and nothing goes below that. But now I'm going to get my 5 volts. So your amplitude is always going to stay the same. So you're going to set your amplitude, so we'll set it up as 1.5 hertz. Might be a little slow, but we'll try. Yeah, you can see how slow, you can kind of see that thing. Turn up my. So you can see that thing's going up and down. So what it's doing is it's watching this thing and it's going up and down. So what it can do is that it can adjust my time, because my horizontal movement is my time. So I can slow down my time. Now what I did is because it was trying to put in this, my horizontal is my time, and what I did is I gave this a much more time. Now I got 200 milliseconds per division. So now I can see even though this is still at 1.5 hertz, now I can see it just by adjusting my time. Okay. And we're gonna go through this a lot more thoroughly tomorrow. But just to get you guys going in digital and give you guys kind of a understanding what's going on. So what I did is I just increased the time. It's this amount of, how much time am I sampling? Like if I'm watching something that's 1.5 seconds long, and if I only have it as 1 second, I'm going to miss half that signal, right? So what I did is I just said, over this amount of time, give me about 5 seconds. So that's what I'm kind of doing here. All right, so here's our 1.5 hertz. And then right here is my 0 volts. Okay, so you can see that half is above it and half is below it. So what I'm going to do is I'm just going to go over to my DC offset, and I know that I want 5 volts, so I'm going to set this up to 5 volts peak. So we know that from here to here I'm going to have 5 volts peak to peak is what I really want. So I'm going to set that my volts peak to peak up to 5 volts. Now you can see that my amplitude just got larger. I'm watching it, all I'm doing is watching it, so I'm not doing anything with my oscilloscope, I'm just changing everything on my function generator. And then I'm going to adjust my DC offset so that half this voltage gets raised up. So I'm just going to add another positive 2.5 volts up to it. Now what I have, here's my 0 volts. So what's going on now is it's running along, and all of a sudden it goes up to a positive 5 volts, then it goes down to a 0 volts. Up to a positive 5 volts, down to a 0. So that's all you really need to do. Okay?
That's close.
Yeah.
How are we supposed to, now we gotta go home and build this in 3 hours. How are we supposed to do this with them teaching like this?
But do you sleep at night?